well, I won't make a long introduction, but if you have not checked his web page, please do it. It's full of amazing information. And if the course is half as clear as the information you find on his web and blog and everything, and all his amazing books, then I'm sure it's going to be great. Boaz, you have the floor.
Thank you. Thank you very much. So, yes, hi. So I tried I didn't know what to do the first slide, so I tried to have to ask DALL-E to generate a good slide for me. So obviously we are going to see, we're going to be talking a lot about fish in these lectures. This is apparently you really cannot understand deep learning and computational complexity before you understand fish. And, yes. Yes. Yeah. This is apparently how this course should be conducted.
I like the textures.
Yes. Yes. Yeah. I mean, I guess if you're deep, it's deep. You're very deep. This is like three layers. I guess the.
What is the last one about though?
Yeah, that's. I'm afraid to ask. Yes. So in this, by the way, I also tried later something they did nicer.
Wow.
So.
Wait for the T-shirt.
Yes, yes. The computer would have won the T-shirt. Yes. So I'm going to be talking about a little bit about complexity of inference problems and touching a little bit on deep learning. And it's one of the things I hope that you'll be very interactive and stop me and ask questions. I really prefer, it's better if we go slower and we talk a lot than if we rush through. Some of these aspects might be especially the deep learning part might be more, some of the questions people might have might be more of philosophical and general type of discussions. And for those, I am around. I'm also very partial to beer and wine, and will be very happy to continue these kind of discussions over beer or wine. And so feel free to approach me and talk to me. I don't bite. As long as you don't stand between me and that cheese plate in the dinner, then you're safe. If you don't, that's it. Okay, so the plan for today. So I'll do a brief teaser on deep learning, but that would be really more, not really showing things, but showing some pictures. And again, maybe the discussions about that part would be best off to over some drink of your choice. Then I'll talk about signal plus noise type of problems, where the plus doesn't have to be literally taken as a plus, although sometimes it is. And the general conjectured behavior, and this is the type of conjecture for these problems is this shown by this nice figure, which bonus points to someone other than Lenka and Florent who recognizes where I took this from. What? Yes. No, it's from their survey. Yes. Yes, exactly, yes. So the behavior for these signal versus noise problems is typically you have some kind of parameter that's given different names under different circumstances, but you can think of it as the signal to noise ratio, or amount of information in the measurements. And when it's too small, often it's impossible. And when it's very large, then it's easy, and we have algorithms for it. And we conjecture that sometimes there is an intermediate regime where it's possible in principle or in exponential time, or sometimes we say information theoretically possible. The information is there, but we conjecture that there exists no efficient algorithm, and including deep learning, that can achieve it. And we'll talk about this more. And so this general plan for today, this part will be on PowerPoint, and then I'll move to the Blackboard and talk about likelihood ratio and chi-square divergence. And the next lecture, this will be information theoretic. The next lecture will talk about low degree likelihood, which is a very general framework that has been recently put forward to try to predict where this, well, I have this thing, where this threshold might lie. Okay? But before that, let's do some kind of a bit of speculations, discussions on deep learning, and again, very welcome more discussion and over dinner, etc. So here, I mean, I think different people disagree I think with deep learning, I think everyone disagrees on everything, including what are the questions even that we should ask, and what are the mysteries. So I'll give my own list of mysteries, and some other people might have their own. So generally, like you say, in deep learning, we get some data. We have some model family, right? So we have some set of functions, say, that are parameterized by some theta. And I'm not sure even if I'm going to stick with this M. I guess, yeah, whatever letters I pick throughout these lectures, I'll be sure to annoy some of the people and probably please no one. So yes, feel free to each have their own table of M, N, P, etc. So yeah. Ignore the numbers. I'm not sure if I'm going to be consistent with these things later. So, but generally, training, we pick a loss function, and then we use gradient information to search for a minimizer of the loss, like the loss which is the sum of the loss over the training samples. So that's the general thing. So one mystery is often this map that takes the parameters to the loss is non-convex. So how can we find this minimizer? So this is kind of the computational mystery. Another mystery is often we are over-parameterized. So if we are over-parameterized, what kind of guarantees do we have over the loss on new examples that we didn't see before? This is kind of the statistical mystery. There is more, but one, for example, way to say that, like, is even regardless of whether M is larger than N or M is smaller than N, it's not clear what are the guarantees. We are not going to use, in truth, that even this is not really what we care about. We are going to use it in some kind of another setting on the data that is somewhat different, or sometimes even on tasks that is somewhat different. So transfer learning or out of distribution learning. So what kind of guarantees do we have on the performance of the network where we are actually going to use it for? And the general answer is we can't guarantee that we'll find theta star. We have no guarantees on how it will behave in the over-parameterized setting, and we have no guarantees on its performance. But yet, often in actuality, things work out. We do find a good minimizer. It does work well on fresh examples, and it does even transfer to things that are outside of what it was trained on. And of course, you know, sometimes we even have theory that explains part of it, and some of it was shown by Nati. But maybe for me, somewhat a bigger mystery to me, in some sense, is that to some extent, you know, it's even what's going on in deep learning is not even exactly learning in the statistical sense. Or not just that, maybe some other things. So let me try to, again, be a very high level, and I'll kind of return to these points maybe at the very last lecture. So most of my lecture will be on more precisely defined math. So generally the way I view kind of what is statistical learning. So statistical learning, the way I view it is we're doing some kind of, say, function approximation, and more generally it doesn't have to be a function, could be a distribution. So we get some samples from some domain, we get some samples, some of them are red, some of them are blue, or maybe it's a number, or maybe some other label. And then we try to find some function that approximates on the domain. And basically what we are trying to do is we're trying to learn a black box. So typically in statistical learning, what we think about the object that we're trying to learn is ultimately some function that maps inputs to outputs. And the property that we're trying to do is that we are given some samples, and it should generalize to fresh samples from this distribution. So somehow we are given some queries to some unknown function, and we are trying to approximate it. And that's typically how we understand what deep learning is doing also. I mean, it's almost, if you look at the code of, say, a deep network, it's basically the same as the code for, say, linear regression, which is, or the same as the code for anything. It does exactly this, right? You're given some samples, the points, and you're trying to, you're running some optimizer to try to find the minimum, some kind of minimizer of some loss and regularization over these points to hopefully find an approximation for the points. But I want to say that maybe this is not exactly, even though this seems to be what we're doing, maybe this is not exactly what we're doing, or at least not only we're doing. And let me say, what do I mean by kind of non-statistical learning? And I guess the kind of non-statistical learning, I think, like, think about how you teach a human, like you guys, or say young kids. And what they're really learning, they're not learning, you're not teaching a student to approximate a function. So for example, if I am trying to teach, so if I'm trying to teach, say, my kid to multiply numbers, then typically, I guess most people, they don't just, they don't sample random, they don't sample random, random equations, give the kid a candy if they do it right and a slap if they do it wrong, and, and teach them to approximate that function, right? This is not really the way most of us, I hope, teach our kids. But rather, we kind of, we actually might not even, we somehow build these skills and the internal representations, and they are not really even training on exactly the thing that they will be necessarily, say, tested on. So somehow what seems to be going on is you try to find some tasks for the kid to do that will be kind of hard enough that they are evolving, but not so hard that they are impossible, right? So if you teach like a 10-year-old kid, you're not saying, okay, integrate whatever this and that. I don't even know what to write, but whatever. Compute this partition function. It will not be useful. So during COVID, I started this exercise program, watching videos and doing some home exercise. So the trainer on the videos would say, pick a weight that will challenge you but not break you, right? So this is what we're trying to do with kids. We basically try to find the tasks that are exactly hard enough for them to be out of their comfort zone and evolve whatever internal representations of skill. And in particular, we don't really think of the kid as a black box, and we don't even care so much about the black box performance. And these tasks, we don't really care about them for their own sake, but more about what kind of skills they develop in the child. And to some extent, I want to say maybe part of deep learning might be looks more like the right-hand side than the left-hand side. So in particular, when we're doing, say, when we were, say, training, say, large language models for, or any kind of models on large unsupervised training, we can pick various loss functions, but we don't really care about that particular task that we are training them on. We are going to care how they are going to transfer over to some other tasks. So the only goal for that particular task that we are training them on is for them to develop representations. So yeah, and I think to some extent you can see, and again now I'm just going to flash some figures, and we'll maybe go back to these some of those things later on in the week. But say we've had some experiments where you could see that somehow as you're training a neural network, you can kind of explain its performance initially by, say, in this graph we don't see the best linear model and then like the best shallow model, and at some point it kind of surpasses until it surpasses like the threshold of, say, the best. Until it surpasses the threshold of like the best, the best, say, CNN2 model, it's kind of close to it. Yeah. I mean, these in these graphs, these are like a little bit less than I would like. Or another kind of experiment say that sometimes you change some parameters, and there are similar things with batch size that I think Nati mentioned. That say you use a small batch size or a large batch size, and sometimes one of them you optimize earlier, so you do better on training, but somehow maybe the task wasn't hard enough, and then you do worse in test. So sometimes you have some transformations that you can make to your parameters that somehow seems to have the effect of trying to make the task not too easy. And there are like some other things that you can think of skills. We had this paper where we tried to track what happens as, say, you're training a network in terms of its predictions on a, say, in particular sample. So you can look at this sample and look at what are the predictions of the models as they're training, and on the x-axis is the global accuracy of this model. So as the model becomes more and more accurate, you can see that it learns that with higher probability, higher confidence, that this is indeed a coffee mug. Although already in the beginning, it's pretty sure it's a coffee mug. And then if you look at this coffee mug, where we had a picture of the Dalmatian on the coffee mug, then actually initially the model really gets thrown by the Dalmatian, and only later on it kind of figures out that the global structure is more important than the local structure, and identifies this as a coffee mug. And to some extent you could say that the skill of understanding more global structure might be picked up later than the skill of recognizing objects from texture.
But still you will have the result and the answer will be a cup, right? Or it's
No, here, like, for example, it will answer Dalmatian. The probability of Dalmatian is higher than the probability of a cup.
okay, but that's the coffee mug. The cup is the pink one, the highest one, right?
The cup, but yes, cup, coffee mug. Yes, so cup and coffee mug, let's say I consider them as good, and as both equally fine. But the Dalmatian, you see, it's very large here and goes down significantly here. So,
Okay.
yes. So, yes, so this mini course I'm going to do, yeah, I mean, I don't know if primary is even a word for it. I'm happy to go into more details on computation complexity as needed, but we'll mostly talk about the second point. So this will be maybe the most, what we'll spend most of our time on these notions of computational versus statistical trade-offs, with the understanding that this is maybe not the whole picture of machine learning, of what's going on in deep learning, but I think it's part of the picture. And maybe there is really no theory that explains the whole picture. But we'll, again, talk maybe at some later, and for here I even show these pictures without saying what they mean, but we'll talk later about how we see some of these thresholds that we see, we kind of see them when we train deep networks. Okay, and so with that, let me start with talking about, or maybe before I start. So any general question before we start doing math? Okay, so people are eager for math. So, okay. So let's start with a picture of worst case computational complexity. Just to get a sense of the room, maybe how many people here have heard of P, NP, etc.? Okay, everyone. Everyone, good. So let's do what?
How many solved it?
How many solved it? Yes, that's probably also everyone at some point. Yes. So the general picture, right? So we have the class P, and there's a lot of problems for which we have polynomial time algorithms. Then we have the class X of everything that we can solve in exponential time, and which is a superset, obviously, of P. And then there's these problems which we don't necessarily know if they are in P or not. So we believe they are not. So all sorts of problems we believe they are not. And for some of them, we know how to verify a solution if we get it. That's usually the problems we care about. So kind of optimization problems. And the class of all problems for which we can verify the solutions is called NP. And then there are some problems in that class which are known as NP complete, which is that these are problems for which if you had a worst case algorithm to solve them on every possible input, you will also have a worst case algorithm to solve every other problem in NP. So all of them, and also factoring, etc., in polynomial time. Okay, and all of those relations are basically conjectural. We don't, when we know containment, but we have no, generally in computation complexity, we have no lower bounds. We don't know that anything is outside of anything. Someone might say that we do know that P is different from X, but even that is not exactly the case because, yes, we know that there is something known as the time hierarchy theorem, so we know that P as formally defined here is different from X, but often we care about having polynomial size Boolean circuit, which is sometimes known as P/poly. And if we talk about P/poly, we don't even know that it cannot do everything in X. So basically, we don't know anything. And our focus is going to be on average case variant of these NP complete problems. And again, it's very important to understand that the fact that the problem is NP complete means that it's hard on the worst case. It doesn't automatically say anything about how hard it will be on any particular distribution. So for a particular distribution, it could well be the case, and it is the case that, say, if you take a problem like 3-SAT, it could well be the case that you can change some parameters. So if you have some families of distribution, then it could be the case that as you modify this, say you have a parameterized family of distribution, that as you modify this parameter, you move from a case where there is a polynomial time algorithm to a case where no one is known and no one is believed to exist. And often what happens in these cases is that we see a type of threshold behavior where in one range where of the parameter space, not only there is a polynomial time, there is often like a linear or really very efficient algorithm exists. And once you go above that threshold, not only there is no known polynomial time algorithm, there is no known algorithm that does better than exponential. So it seems that the complexity kind of jumps basically from linear to exponential. Okay, so now what kind of evidence do we have that these problems are hard? So we would like to have unconditional mathematical proofs. And one thing that is important to understand that it is a well-defined mathematical question. So the only excuse not for us not to have mathematical proofs for everything that I showed before and that for things is that we are stupid. But we are stupid. So we don't know how to prove any of those conjectures, but there is no, there are well-phrased mathematical proofs, mathematical questions. So the question of the computational complexity, say the smallest Boolean circuit that can, solve 3-SAT on the worst case or on any particular distribution, that's a very, well-defined mathematical question that has a yes or no answer. We just haven't been able to prove it. So we give up of the proofs. And so now one thing people can do is use reductions from other assumptions. So we say, okay, we need to make some unproven conjectures. That's just life, but let's try to minimize the number of unproven conjectures that we make. So, and we have this shining example from the theory of worst case complexity. So in worst case complexity, you make one conjecture that P is different from NP, and tons and tons of things flow from it, and you get basically a full, like a full picture and a nice characterization of essentially almost all problems that you care about, whether they are in P or not in P, based on this one conjecture. So this is an area of study that people do, but often this is not so successful in average case complexity. And one reason is that the reductions in average case complexity have much less room to work with. So basically, if you're trying to do if you're trying to do a reduction, say, how does a typical reduction look like? Maybe I'll use those fancy chalks that I bought. Otherwise, it will be right. So how usually does a reduction looks in computational complexity? So you have problem A, and say input length n, and you have these two parts. The yes, say it's a Boolean problem, it's a decision problem. The yes instances and the no instances. And what does a reduction typically do? A reduction is a map from instances of problem A to instances of problem B, which typically will be, so you have this problem B, and you'll have like on size, input size m larger than n. And you have here the green, and here is the red. And the reduction typically, the way it will work is if it maps this into some subset here, and this maps this part into some subset here, then it's a valid reduction. If you had an algorithm that could decide whether an instance of B is yes or no, then you have an algorithm that can decide A in the worst case. You would take this input, you map the reduction, and then you make the decision. Now, you can see in this picture that this kind of a reduction will typically, even if if the instance here was uniformly distributed, here you would get something that's pretty ugly, like distributed on some small subset. And typically this is always the case, like because you would, if the reduction has any kind of blow up, and it almost always has one, because if you say take a graph and you add some gadgets to it, so suddenly you take a graph of say n vertices, and now you have a graph of 3n vertices. So you moved from a set of size 2 to the n to a set of size, okay, let's ignore, let's say graphs on n vertices are n bits long, whatever, 2 to the n to a set of size 2 to the 3n. So it's a very, you are like in exponentially small, so typically the support of, even on the uniform distribution, it will be like on an exponentially small subset here. And again, there are some ways people have been trying to do sometimes average case reductions. It's not that it is impossible, and some of those exist. It's just hard, and maybe not always possible. So we don't have such a rich theory that you start with one axiom and develop everything else in average case complexity. Yes, please, thank you.
But in some cases, we have average to worst case reductions, right, where this problem won't be.
Right. So some cases you have very yes. In some cases you have that's a great thing. So some cases you have you can say you have an algorithm that basically, given any particular, say, point here, so maybe I should draw this point here. Given any particular point here, it can randomize it, so it will it can randomize it everywhere. And that it will stay in the red side, and if it was in the green side, it will stay in the green side. And if you have such a reduction, then you basically can start with this reduction, then re-randomize this thing and get and now if you had an average case algorithm for B, you would have a worst case algorithm for B, and then you'll have a worst case algorithm for A. So sometimes you do have these things. Typically, these problems seem to require a certain structure that we not always have, and there are some results in computational complexity suggesting that maybe you could not have this for NP-complete problems, and generally this part of this is a question that people have been very deeply interested in. Part of it is because the hope would be to base cryptography on the sole assumption that P is different from NP, and we don't know how to do it, and that's part of the reason. So another thing we could do is basically try to have proofs for restricted computational models. So there you say, okay, I conjecture that all possible efficient algorithms cannot solve this problem. So in particular, a prediction of this conjecture is that all algorithm of some class C cannot solve this problem. So let me try to verify this prediction. In that sense, I think it's somewhat of a physicsy maybe things to do. You say, okay, have this conjecture, and it makes certain predictions. Let's try to at least verify that these things are true. And this is something we'll talk about a lot. And another part where people also do is to try to look at certain features of the problem, and maybe again, so it will be kind of a combination of conjectures and calculations or proofs, where you would say, I might conjecture that certain geometrical features, when the problem changes a parameter under the geometry of the solution space changes, that would cause computational difficulty. And now I can try to verify that this actually happens in the regime where I think it happens, and I could also try to at least show some relations between these two things, right? So some show that when it happens, some algorithms fail, or maybe at the regime that some algorithms fail that I already computed in another way, that these kind of changes happen. So and generally, if say all of those, say for a particular problem, right? So if you have a particular problem, okay, maybe I actually need, I don't know how to do color on the iPad, but so I'll use it. So if you have a particular problem, and basically we have our algorithm go up to this regime, and at this point we see that say at this point we see that several different families of algorithm all fail at this point, and maybe some geometry of the problem changes at this point. then we say, you know what, we conjecture that this is the right threshold, that this is really where the problem changes from being easy to being hard. And yes, do you want to say something, Nati? Okay. Okay. It's like a big question.
Well, I mean, it changes, or we need different techniques, right? I mean, you're showing
Right.
our techniques fail, right?
Yeah. So I'm saying this is not proof, but yeah, this is not a proof. But some of this is basically sometimes maybe as good as close to proof as we get. So I mean, so it seems reasonable to conjecture as a working hypothesis that at this point, if several of our if several techniques all stop in the same point, and these techniques seem to be optimal, in other problems that are similar, we don't know how to beat them. So people have started trying to formulate these conjectures that certain families of techniques for certain families of problems are optimal. And there are two reasons why I like these conjectures. One reason is that it's quite possible that they are true, and they are giving us a good picture of where this difference between easy and hard happens. The other thing that's nice about these conjectures is that they are very, very far-reaching. Like, so you have these conjectures, say, about the low likelihood ratio, that is very far-reaching and it's very ambitious. And the nice thing is, when you have a conjecture that's very ambitious, it's like putting a very big target on your back, because it's very, you can try to refute it in many different ways. And the bigger the target on the back that the conjecture has on it, and the longer it stays alive despite having this big target on its back, the more I feel like maybe this conjecture is actually true. And yeah, so right, and yeah, I mean, yeah, like think about it. If you, if I wanted, if my conjecture is that there doesn't exist a minefield out there, so what would be a better proof for it if someone were to go there, put one step in and go back, or someone were to go running around all of it wildly, waving wildly? Then yeah, probably if the person is still alive, maybe there isn't a minefield. Or yes. Okay, so right. So our focus will be on this in these lectures will be on the problems that are in the planted regime, or sometimes called. So you have a kind of a planted distribution versus null distribution, or you can think there is a signal versus a noise. So generally we'll have some signal u, which is distributed according to some distribution mu. And we have some probability over the observations we see, which is the observations that we observe if the signal was equal to, sorry, not mu, equal to u. So these are the observations we see. So we can define the probability distribution P is the mixture model that you get, where you sample the signal according to mu, and then you sample the observation according to pu, and you look at the observation. And Q will be, I'll call it the null distribution, that has no signal. And this will be the general setting that we'll be looking at. And the kind of tasks, you can have several tasks that you can consider in this setting, but like maybe the three main ones will be the following. One is hypothesis testing. So you're given an observation, you want to distinguish between the case that it came from P versus the case that it came from Q. And we can look at strong, where the errors go to 0, and weak, where the errors say at least less than 1 minus epsilon. So at least you can do something. And so we'll sometimes consider one, sometimes the other. So the errors, I mean, like you can think of type 1 and type 2 errors, the probability that you get a sample from P and think it's Q, and the probability you get a sample from Q and think it's P. And if the sum of the errors is bounded away from 1, it's a weak distinguisher. If the sum of the errors goes to 0, as say you go with increasing, say, there is always going to be some parameter n somewhere lurking around there, so then you think, then it's a strong distinguisher. So the estimation problem is to recover u, and sometimes you cannot recover u exactly, but maybe you recover u prime that is close to u in Euclidean distance or some other appropriate distance measure. So the recovery problem is, you're given y from pu and you want to recover. The refutation is to certify, given something that is null, to give like a certificate, a proof that it's null. So if you get u prime, it's kind of a proof that you are in the planted distribution. So you can also think of getting a proof, and sometimes we can do that, but get a proof that knows that this was really from the null, again with some good probability or high probability. And if you can, the hypothesis testing is the easiest of those three. So in particular, if that is hard, then both estimation and refutation are hard. And these can be sometimes incomparable, although in several settings it seems that the threshold is the same for all of them. So approximately at the same point, you can, there seems to be a case where when the signal to noise ratio is below a certain value, then you cannot do none of them, and when it's above a certain value, then you can do all of them. Or at least sometimes it's not maybe precise threshold, but the general vicinity, the same general vicinity. Yes. Yes.
Here you observe P, right?
Yes. Observe a sample y from P. Yes.
So what does it mean distinguish between P versus Q?
So no, in the hypothesis testing, you observe a sample that with probability half it came from P, probability half it came from Q. So hypothesis testing, you given F, which is from the whatever space of observation is, let's call it script y, to P Q. And now you look at the, say, type 1 error is the probability that f of a sample from P is equal to Q. And type 2 is the probability that f of a sample from Q is equal to P. I'm pretty sure this is the ones, but it might be I got them all wrong. But in any way, I'm going to sum them both together. So this is a distinguishing problem. So you want the sum of these errors to be less than 1.
So basically, you have access to Q.
You have
It is a theoretical thing. So what do you have here in your hands?
an observation that was sampled from either P or Q. You don't know.
Okay, so you only have the samples and...
You know the problem, right? You know that the probability distribution, you know the probability distribution P, you know the probability distribution Q.
Okay.
Okay, so you have a null model, which is Q. You have one way to think about it, right? You have a null model, which is Q. And you have a sample which you believe actually might have come from P. But you want to certify it. So how do you do it? Like there is a place where you have like an actual refutation, but or you can actually recover U prime. But suppose you don't necessarily know how to recover. You have this distinguisher, and this is basically the same as saying, if it was sampled with probability half over P or probability half over Q, you'll have some. So there is two measures. You can have a weak distinguisher will have some advantage over half. A strong distinguisher will have advantage basically going to 1. So basically will tell you whether it's from P or Q. Okay? Yes?
Do the support of Q and P have to be separate?
Not always. Obviously, I mean, again, like these problems, they might be impossible, right? So you might have been in a regime where these problems are not simply computationally hard, but they could be impossible. To solve, say, the refutation problem, you need that with high probability. You need that with high probability over Q. You're not in the support of P. But you can also think of like some softer version where you may want to certify that the, say, minus log probability of y under p is really, really large. Say, unreasonably large if it actually came from p. So you could think of these kind of things. Okay. So the signal plus noise model. So in the signal plus noise model, we think of the following, and again, like think of it as a simple multiplication and addition, but generally, it could be some other ways to combine these two objects. So you have you observe you observe the distribution. You have a distribution p lambda, where the observation is you take lambda times the signal plus noise. And so if P0, there is no signal, so it's null. And P infinity, the noise basically cancels out, so vanishes, so there is no noise. So basically, this is kind of the model you can think of as, and again, you can have other ways to combine lambda, s, and n in ways that will give you this, give rise to the same type of qualitative behavior, but generally you have some kind of a signal to noise ratio where if it's set to 0, then there is no information about the signal, and if it's set to infinity, there is all the information about the signal. And general kind of behavior that you'll see in these type of problems is that, say, if you measure, so you can have like this lambda. And sometimes in statistical learning, you would think of it as the number of samples. The more samples you observe, the more signal you have. Sometimes if you look in statistical physics, you can think of it as the inverse temperature, this lambda type of thing. And so you could think of the system as being very hot, where there is no, the signal to noise ratio is small, and very, very cold when the signal to noise ratio is very high. And now you could measure, say, the conditional entropy of the signal. And there are some other kind of related properties, like the cross entropy between the cross entropy between the P0 and P lambda, or the free energy, which you can think of like as some expectation of the log of probability of P lambda under P0, expectation under P0. But anyway, let's think of this for now, like just say the entropy of the signal condition of the observation. So generally, the more lambda is bigger, the less the entropy. And at some point, let's say the signal will be completely determined, and the entropy will go to 0. So it doesn't have to necessarily have a threshold. Let's just say in this example, say some example where it has. But generally, as you make the system colder, the entropy of the signal will drop and eventually goes to 0. And when it goes to 0, that means that you can recover the signal. You can fully recover the signal. And if it's very large, then you cannot recover it. And then there are like sometimes it's more fat in the middle, but I'll say something about it in a second. But so there is this, from the same survey, there is a very nice diagram of a problem like that by Lenka and Floran. And there, what you see is that as you plant, this is a random graph where you plant a coloring, and when the signal to noise ratio is very large, you cannot really identify the planted. You cannot find the planted coloring, and you cannot even distinguish. You could not even distinguish between a random graph and a graph in which you planted. It will look the same. At some point, there is actually, you could get some decent amount of information about this point, and eventually you can kind of really figure out the point essentially precisely up to in graphs there might be always some isolated vertices that make it a little bit. So in some sense, this kind of threshold there might be more like a band where you get some information and you get all of the information, but eventually, if the signal-to-noise ratio goes up, you can recover completely. And so generally, we'll say, okay, there is some threshold or some regime where it's not possible to recover, and some regime where it is possible to recover, at least statistically. And what we care is, is that there seems to be this intermediate regime where it's possible, but it's hard. We don't know how to do it. And then there seems to be some kind of a computational threshold where it becomes easy, where we can actually solve it. Yes, you can want to ask a question?
I think it's really that, but like I still understand despite your explanation why in the left regime, an impossible regime, the entropy still goes down. Like you can actually you can like you can identify. So maybe you can't recover exactly S, but you can definitely tell whether S is in there or not, right? Based on just looking at your plot, right? When the entropy is so low.
Right. So you're right that basically there should be yes. So it's So statistically impossible here. It's recovery, but generally, like in these kind of problems, there might be some different. There might be some regime over there where it's where you can already partially recover, but not get some partial information about it, and not.
Okay, so you're really looking at
right.
Exact recovery.
No. I mean, in some sense, I'm not looking at it at all. So I want to say yes. So basically, also inside here. There is also like these two other, there is this other question which, let me kind of skip to most of our time, just also to kind of get a sense of where things are going. Often this part is often much wider. So just to kind of get a sense of, so Nati, maybe to get a sense of like the scale. So for example, for many problems like random constraint satisfaction problems and etc., then here, when you're talking about this threshold, you ask whether it's 4.21n or 4.25n, etc. This threshold is like n to the 1.5, and you don't care so much about like the minor differences between whether it's n to the 1.5 times. In some sense, it's not even well defined because then you start talking about the exponent of your polynomial. So in some sense, this figure is not to scale, and it in some sense cannot be drawn to scale in the sense that this regime, this place is usually much wider. It's just on a different level than this regime, and our focus is going to be here. So we are not going to quibble so much about where exactly this thing happens and in what sense it happens. Like for us, yeah, you're right that the constant in front of the n where it happens is a little bit different depending on exactly what you're trying to do. But we are not going to quibble so much with exactly where it is because it's kind of negligible compared to where this thing is. And I also want to make sure that there is a source of confusion because there are two computational thresholds, and I think maybe some of the lectures were so even in this regime, you can talk about you ignore the planted problem. You can talk about the random problem, and the random problem also often implies some kind of an Hamiltonian that you can try to optimize. And there, it's kind of interesting that it's actually the opposite. The hotter the problem, the easier it is to optimize this Hamiltonian. So there you have a different computational threshold. And one of the confusing things about this whole literature is that sometimes people, I think, get confused with these two different regimes. So you have random problems where there is no signal really. The random problems, say you have random, if you look at literature on random SAT, etc., typically there is no signal. You didn't plant anything. There is just the natural, say, satisfying assignment that the SAT formula has. And generally, the hotter the system, the easier. So there is a threshold where there is no more assignments. But before that threshold, sometimes there is a place where the assignments exist, but we don't know how to find them. And then as you go hotter, then it becomes easy. And this is a completely different regime than this regime of planted problems. And in particular, for example, in the what's the name of the Hamiltonian that Montanari optimized? What? Sheridan-Kirkpatrick. Yes, the SK model. SK model, this part doesn't exist. Andrea showed that random is easy all the way here. But this part still exists, as far as we can tell. As far as we can tell, it's still hard, say, to, for example, to certify that, for example, to certify that there is at most that you cannot do better than 1.8, like, right? So there kind of there is a regime where this is kind of at 1.5 something, and this is at kind of 2, and as far as we know, this is still hard. The questions, or so basically, our focus is going to be on this. It's not that this is super interesting, but our focus is going to be on this part. Yes.
Would it be interesting at this point to go back to the deep learning and relate it to the interpolation threshold?
Okay. So I think I'm going to go very quickly. Yes, next slide. You're anticipating the next slides in some sense. So maybe then we can go back and talk about these things. But I don't know if I'll relate it very formally. But let's talk more about it in the next slide. So no, that's good. So our focus is going to be mostly on this part, on this general part, and so we are going to focus. Say, for example, if you're looking at random problems, typically, they undergo these transitions where they, initially there is one. Like just one convex kind of set where the solution space, then they break, and then they get into, so I think this is the dynamic, and this is the static breaking, or at least, or do I get it confused, the other way around? No? And then they completely disappear, so our focus is like way after this, nothing interesting as, way after kind of nothing interesting as is happening. So we are basically going to focus mostly on this part where after things are interesting. And yes.
About that random easy part, is it right to think of it as like it's becoming easy due to some kind of universality or like some smoothness? Because like why do you have any intuition for why that part exists?
So generally, okay. So I guess the question is, in some sense, what to define. What is the task here, right? So the task there is typically, you don't think of it as finding the signal, but as say finding some minimizer of an Hamiltonian or something like that. And the closer you go to here, at some point, like it's just a flat line. Everything is a minimizer. Like to some extent, the more the closer, maybe one way to think about it is this entropy going up and up. At some point, if you just take a random point, it would be yes, and that also has to do, maybe part of it with Nati is I kind of, this line can plot different things. And some of it is the entropy of the signal where you might have these things, and some of these with this free entropy, etc., they could be going down without, so there are several curves that behave like that, and not, and some of them, they could be going down without allowing you to even potentially, yeah, so. Yes. So deep learning. So Lemka, this is for you. Often, maybe what happens is the following: you have, say, some training data, and maybe you want to look at, say, the entropy of the labels. You want to find, say, the minimum, and doesn't have to be the actual minimum, the minimum that you actually find. So you want to look at the entropy of the labels that we condition on your predictions. And as you, say, increase some parameters, say, for example, think of the model width, eventually the problem becomes definitely easy enough that you could get this to 0. So you could say, you know, there is a certain way. Oh, sorry. Let's say this is the actual minimum. So there is a certain say if the size of the model or some is too small, then you simply cannot interpolate. There is no way to fit a train. If the model is very big, then it's easy to interpolate. And then there might be some different regime where it's possible by hard. And again, like maybe in deep learning and in sometimes general, whenever we say computationally hard, I drew it as red, but often in these cases, it's not really often as sharp or threshold. It's really quantitative. It looks more that, you know, if you plotted the running time, it will go higher and higher and higher. But you know, it's a smooth thing. It's not it's not exactly in these things often jumps. And in deep learning, it seems possible. And this is at this point, this becomes like a little bit of speculation. That sometimes what happens is, yes, this regime is too hard. You cannot even interpolate. Sometimes with width, and maybe sometimes not, but sometimes this regime could be like when you make the model say too wide, it could be too easy. You can you know it's like my trainer said, you have to pick a weight that challenges you, and I think I think he might have meant weights that you actually lift, but maybe he meant weights for the neural networks. So they have to pick weights that challenge them. You cannot just pick you know. So say for example, you know, you take something too wide, it becomes a kernel method, and yes, it fits the training set, but it's not really learning. So it might be the case that you really need to kind of figure out when you set your hyperparameters, so that you have like this narrow band where things are hard enough that you don't, you know, training doesn't explode. If you go to the left, then training will be, you know, will explode. If you go too much to the right, then it will be too easy, and you find kind of the nice sweet spot. And again, like this is not, we have these nice double descent curves, so sometimes you can grow size, and you have to be a little bit careful. You could, as long as you don't make your problem too easy, in some sense, if you made your training too fast, then you've done something wrong. But as long as you made your life difficult enough, it might be still, you're still learning. So I don't know if that helps or not, but this is maybe one way to try to kind of relate, and maybe we'll see later in the week some examples. So the rest of these lectures, I have a lot of plans, but I don't know how many of them will materialize, and most of it will be, you know, trying to talk about. So most of it we're not going to see deep networks for most of it, and we're going to talk about just problems, rather, you know, problems and methods. So and classes of methods, and trying to see where is where do we have these thresholds. By the way, how much time do I have?
Still have half an hour.
Half an hour. Okay, good. So we'll get a little bit on the board. Yes. So this is basically mostly for Friday, but and I'm gonna do some of those things, and I'm gonna start today with just talking about hypothesis testing, define it more formally, and define the likelihood ratio. And then tomorrow I'm going to talk about low degree likelihood threshold, likelihood ratio, and maybe do a little bit of a digression to hypercontractivity, noise stability of low degree polynomials. By the way, just to get a sense for planning for tomorrow, how many people here have seen hypercontractivity of low degree polynomials? Small minority, so yes, so we'll do that. Okay, so maybe with that I can move to the board. Okay. Okay, so maybe we'll start. Yeah, we don't need these reductions. Okay. So we're going to focus now, for much of the time, we're going to focus on hypothesis testing. So we have 2D probability distribution. So these are two probability distribution over some space. If I ever have to specify the space, it will be R to the something. Let me avoid picking a letter until I absolutely have to. I want to have someone to sit with